All right, we're going to begin today kind of forecasting backward a little bit. I got a number of questions from you about quantum numbers and about some of the kind of applications and things. I wanted to kind of go back just a little bit just to kind of help reinforce what we saw on Monday and do a couple more examples because that will help set us up for today. So again, with the idea of quantum numbers, what we have to understand, quantum numbers exist to describe electrons. And the 4 quantum numbers increase in specific qualities as we go from one to the next. So that first quantum number, the principal quantum number, that one was all about energy level. So big, broad kind of description. The energy level that this electron exists in is whatever it is. The 4th energy level, the 5th energy level, the 2nd energy level. From there, we start to break it down into more and more specific kinds of ideas. So the angular momentum quantum number. We go from energy level to sublevel. Sublevel being the shape. What shape are those orbitals that hold these electrons in? And so we talk specifically about the 4 different shapes, S, P, D, and F. From shape, we shrunk it down now to the magnetic quantum number. The magnetic quantum number gave us a specific orbital. So in the magnetic quantum number, we were able to say there are this many orbitals inside of a subshell. So for L equals 1, we had 3 different values of M sub L. So that told us that there were 3 orbitals in that subshell. For L equals 2, there were 5 possible values. -2, -1, 0, 1, and 2. Those 5 different values correlate to 5 different orbitals inside of that subshell. And then the last quantum number was the spin quantum number. The spin quantum number told us, is the electron inside of that orbital going this way, spin up, or is it going this way, spin down? And so this establishes that in every single orbital, there are 2 electrons, and those 2 electrons are different from each other in some kind of way. So spin quantum number specifies one of those electrons. The previous number gave us the orbital. The previous number gave us the subshell. The previous number gave us the energy level. Each new quantum number brings us from very general information about the electron to very specific information about the electron. And so with that in place, we are able to answer questions such as this. What are the names of all of the subshells in the n equals 4 shell? So to answer this question, we have to know all of the possible values of L, because L gives us subshell. So if n is equal to 4, the possible values of L can be 0, L can be 1, L can be 2, and L can be 3. Now, how do I know that those are the 4 allowed values? Well, we got to remember our rules. Our rules tell us that we start at 0 for L, and we go all the way until n minus 1. And so if n is equal to 4, n minus 1 is 4 minus 1, that would be 3. So 3 is the biggest that L can be, 0 is the smallest, we can fill in all of the whole numbers in between. Those subshells correspond to S, P, D, and F. Those are the names of the individual subshells. And so those give us the spherical shaped orbitals, the dumbbell shaped orbitals, the cloverleaf shaped orbitals, and the F orbitals, which have a variety of different shapes. For the second question here, how many orbitals are in all of those subshells? The orbital quantum number is the magnetic quantum number, m sub L. And so what we need are m sub L values for each of these. So for L is equal to 0, m sub L is going to be 0 also. Remember, m sub L ranges from negative L to positive L. For the P sublevel, m sub L starts at negative 1 and goes all the way to positive 1. For the D sublevel, we start at negative 2 and go all the way to positive 2. For the F sublevel, we start at negative 3 and we go all the way to positive 3. Now the question was, how many orbitals are in these subshells? Well, how many unique quantum numbers have I come up with now? I have 1 for the S sublevel, 3 for the P sublevel, 5 for the D sublevel, and 7 for the F sublevel. 1 plus 3 plus 5 plus 7 gives us 16 unique orbitals in this shell, in this energy level. Now, in your homework, you were asked a question very similar to this, only it wasn't asking about orbitals, it was asking about electrons. Now, to answer that question, we'd have to go down to the spin quantum number. Each one of these orbitals would have 2 different spins in it, plus 1/2 and negative 1/2. So if each one of these orbitals represents a maximum of 2 electrons, 16 times 2 will give you 32 electrons in total. So the 4th energy level has the capability of holding a total of 32 electrons. Each one of these sublevels can hold double the number of orbitals. So the F sublevel can hold 14 electrons. The D sublevel can hold 10 electrons. The S sublevel can hold 2. The P can hold 6. Now, why that is important is the subject of today's new material. Because in that new material, now we can get into how many electrons are in a given sublevel, and we can start to describe all of the electrons in a given atom, not just the one that is described by these quantum numbers. So one of the last things that we looked at on Monday was the idea of the Pauli exclusion principle. I kind of buzzed through it quickly, so we want to rehash it, restate it here. What the Pauli exclusion principle tells us is that no 2 electrons in an atom can have the same 4 quantum numbers. Every electron has to have a unique set of 4 quantum numbers. Otherwise, we know that that atom cannot be in the ground state. It must be in some kind of an excited state. So the only way we get this one in the middle or this one on the right is if we're in an excited state of some kind. But we can still evaluate the quantum numbers of individual electrons in a system here. So if I was going to give the 4 quantum numbers for this electron here, I would start with n equals 1. So my first energy level, L is equal to 0. That tells us that it's the S sublevel. M sub L also has to be 0 because there is no other option. And M sub S is positive 1/2. Those 4 quantum numbers describe this electron. Now, what about this other electron? Well, it is also n equals 1. It's in an S sublevel, so it's also L equals 0. Since L is 0, M sub L has to be 0. The spin quantum number, here we're looking at an arrow pointed down, so it's negative 1/2 instead of positive 1/2. So the only difference between these two electrons in terms of their quantum number is the spin. They're in the same sublevel, they're in the same orbital, but they have opposite spins. So we can use quantum numbers to describe any electron in an atom. That's the purpose of quantum numbers, to describe those electrons in that atom. But what we'll find is that in a lot of cases, this information isn't terribly useful to us. What becomes more useful to us is information like this, where we're talking about, okay, what is the capacity of an energy level? What is the capacity of a sublevel? This kind of information, which we can find kind of summarized in this table, ultimately can lead us to electron configurations. So before we go there, let's just take one more quick look at quantum numbers. And what I want you to do in this particular example, there are 5 sets of quantum numbers here. Some of them are realistic and could be describing an electron. Some of them could never describe an electron because they contain valid numbers that they contain quantum numbers that are invalid. I want you to choose which ones are which. So there are multiple possible answers here. So give you a minute to work on it. And then we'll go through and talk about why the answers are correct or incorrect. When doing problems like this, the easiest thing for us to do is to look for obvious mistakes. So what I mean by obvious mistakes are quantum numbers that we know can only fit in a very specific kind of window, and finding things that don't match that. So for example, letter C. We have a spin number in letter C that isn't positive 1/2 or negative 1/2. Since those are the only two allowed values for the spin quantum number, and this doesn't have either of them, we know C is incorrect. Similarly, letter E. I've got a negative energy level described in letter E. You can't have negative energy levels, and has to be a positive number. So I can automatically eliminate that one as well. So what becomes left for us and what becomes necessary is, can we evaluate these three based upon their quantum numbers and determine if they are correct or incorrect? So in letter A, first energy level, okay, yeah, that makes sense. L is equal to 0, that's always a possibility. Every energy level has an S sublevel. Magnetic quantum number of -1. Okay, hold on a second. Remember, M sub L, the reason why it is M sub L is because L dictates the terms of it. So if L is 0, M sub L can only be 0, because we have to go from -L to positive L. So -1 isn't in that range. So A can't be right either. So let's look at the other one. B, third energy level, yeah. L equals 2. Remember, L can go all the way to n-1. 3 minus 1 is 2, so that works. M sub L of -2, yeah, if L's 2, we can go from -2 to +2, so that works. M sub S is +1/2, yeah, that's a good one. For letter D, N equals 2, yeah, second energy level. L equals 0, yeah, S orbitals in every energy level. M sub L 0, that's the only value it can be if we're dealing with S. -1/2 for the spin, yeah, that works. So we've eliminated every possibility except for those two. Those two are valid sets. So we can describe electrons that have these 4 quantum numbers as real possibilities. All right, any questions with quantum numbers before we kind of move toward switching it off to talking more about electrons globally as opposed to individually? Okay, so when we talk about electron configurations take us from looking at electrons individually inside of an atom to looking at them kind of broadly, looking at every electron all at the same time, as opposed to that one electron is in this one type of orbital, this one energy level, this one sublevel. Electron configurations generally follow a given format. That given format takes those first 2 quantum numbers, the energy level and the sublevel, and puts them together along with a number written as a superscript to represent the number of electrons in that sublevel. Now, these slides here have an order of filling, and we're going to largely ignore this order of filling, not because it's incorrect, it is correct, but more because we have a better way of doing it other than just memorizing this list. And we'll get to what that way looks like here in a second. But before we get to that, we need to understand that there are two guiding principles that give us electron configurations and help us to make sense of them. The first is something called the Aufbau principle. The Aufbau principle tells us that when we throw electrons into an atom, those electrons are going to occupy the lowest energy level first and build their way up to the higher energy levels. But we're not going to build the next level until we have filled the level below it. So take this for example. I've got two electrons here. Those electrons are going to go into that first energy level, the 1s sublevel, before they split up. Low energy wins. Low energy wins. So we're always going to fill the lowest energy levels first, and then we're going to build our way up to the higher energy levels. That's the Aufbau principle. The second guiding principle is something called Hund's rule. Hund's rule specifically governs how electrons are dealt with when we have larger sublevels. So for the s sublevel, there's only one orbital. So there's only one place for the electrons to go. And so I put one in, and then I put the other one in, and it's filled. But for the other sublevels where I've got multiple orbitals in that sublevel, I need to have kind of a guiding characteristic. And that guiding characteristic is going to be based upon the idea of repulsion. Electrons are negatively charged. Like charges generally push apart from each other. And so what Hund's rule is going to state is that when I have the option to separate electrons inside of a sublevel, I'm going to do it. So in the p sublevel, I've got 3 orbitals. I'm not going to see electrons pairing up inside of those orbitals until all 3 orbitals are filled. I'm not going to see it, because to do so would introduce 2 electrons into the same orbital, and they're going to push up against each other. Whereas if they are put into these orbitals and separated, they're going to be physically further apart from each other and less likely to repel. So that's Hund's rule. Now, Hund's rule really only comes up when we are looking at electron configurations in this kind of format. This is called orbital notation. Orbital notation takes that simple condensed formula and spreads it out to show you where each of the electrons are and how those electrons are arranged. And generally speaking, that really only comes up in conversation in 2 scenarios. One, quantum numbers. If I'm trying to evaluate quantum numbers on these, I already know how to get the N and the L from the orbital notation. Where these orbital lines would go is I would use these to determine the magnetic quantum number. And from the magnetic quantum number, they're always from the negative on the left to the positive on the right. So that's one application. The other application is bonding, where we can use orbital notation to describe how we know that this atom is going to bond in a certain way or another. And that we will get into after midterms, when we get into kind of the second half of this class. So here are the 2 representations side by side. We call these complete electron configurations because they are accountings of all of the electrons in a given atom. At the very end of today, we'll talk about a shorthanded version of an electron configuration which really only focuses on those electrons that are on the outside, on the outer portions of the atom, the ones that are directly responsible for bonding. But for right now, we're going to focus primarily on complete configurations. Complete configurations show all of the electrons and their locations. So what I want you to do right now is, if you have your copy of the periodic table from last time we wrote on them, break it out right now. If you don't have it, that's okay. The notes that I'm about to share here are already in Blackboard in that annotated PowerPoint that's presented as part of Module 3. So you can get all of that information later. You can actually pull it up right now. So if you don't have your periodic table handy, just kind of write notes along as we go, and we'll kind of take it from that spot. So the first thing that I want you to do, and this is just for electron configuration purposes, but I want you to just draw in a temporary box here for helium right next to hydrogen. Now we know that helium has about as much to do with the alkaline earth metals as hydrogen does the alkali metals. The only thing that hydrogen has in common with the alkali metals is that it makes +1 charges. And while helium doesn't make +2 charges, except in kind of extreme cases, the purpose here is a really simple one. I want to be able to highlight these two groups together. And we're going to label this as the S block. So our period numbers here give us the energy levels. The positions here are going to give us the sublevels. So elements in these first two columns are in the S block. Their electrons, their last electrons, are going to have a S designation in their electron configuration. So hydrogen and helium, that would be the 1s. Lithium and beryllium, that would be the 2s. Sodium and magnesium, the 3s. Potassium and calcium, the 4s, and so on. So that's the first box I want you to draw in. The second box I want you to draw in covers this other big group of what are called the main group elements. This is the P block. And again, we can match up energy level to sublevel here. So the part of the P block starting with boron, that would be the 2p block. Second energy level, P sublevel. The block starting with gallium, Ga, that would be the 4p block. Energy level's 4, block of elements is in the P group. The next thing I want you to highlight is what we call the transition metals. So this group of 10 elements here in the middle this is the D block. Now, one important note about the D block is that its position is slightly off cue. If we were evaluating the period and the block, we would call the scandium group here 4D. But we actually know that the D block exists starting in the third energy level. Now, why is it in this position in the periodic table? Well, it so happens that once we get to the D block and the F block, we start to see massive jumps in energy for those sublevels. So in the normal kind of configuration, the S is the lowest, the P is next, but it's not that far apart in energy from the S. Then there's a big jump to D and an even bigger jump to F. Well, what that allows for those big jumps is that other energy levels, low energy orbitals, actually can slide in and be slightly lower in energy than the D block and the F block. And so what we see is that the S orbitals actually are a little bit lower in energy than the D orbitals of the energy group below them. So the scandium period, that's the 3D block. Yttrium begins the 4D. And then it gets a little bit crazy when we get to the bottom here. So that last group that we're going to look at here, I'm going to highlight it in purple. This is the F block. And the F block is so high in energy that it's actually 2 energy levels behind. So that F block shows up here in the 6th row, but it's actually representing the 4F. And the one in the 7th row represents the 5F. Now, why did I not highlight lutetium and lawrencium? Because lutetium and lawrencium, if you actually count, there are 15 elements in this block here. 2 of these elements actually belong in the D block. Why are they presented down here? Source material. Depending upon what periodic table and what source it comes from, some of them will put the lanthanum and actinium in the D block. Some of them will put lutetium and lawrencium in the D block. It gets kind of confusing. What are we going to do about it? We're going to largely ignore it. And what I mean by that is, for the most part, we don't care about these rare earth elements. We hardly ever use them. And if we do care about them kind of in any kind of way, it's as a piece leading to an element we actually might use. So when we're writing the electron configuration of lead, element 82, yeah, we're going to have to go through the 4F and the 5D, but we're going to have to go through them completely. So the configuration of how many electrons are in this subgroup and this subgroup isn't going to matter because they're all going to be full anyway. Electron configurations get really funky when we start getting into this group here and even to some degree some of these other ones there. We're never going to give you an example of a electron configuration that you have to do that involves a super wacky kind of exception. If there are any exceptions that we're going to ask you to do, they're going to be ones that we define for you explicitly on Friday. And so there are 10 exceptions, and we will give them to you explicitly on Friday. And 10 sounds like a lot, but we're going to map them on the periodic table and actually find that they kind of follow a pattern. So how do I use this to give me an electron configuration? That part's easy. Now that I've blocked it off, I just go in order. 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d, then 4p. and so on, and so on, and so on, until I get to the element that I'm actually interested in. And to that point, let's do a couple of examples. So for the complete configuration of zinc, the way that I always start these kinds of problems is I look at what I need to do. So what kind of thing do I need to answer, and where do I need to go? Where am I ending? So for zinc, I need to recognize, okay, zinc is in the D block, and in particular, it is in the 3D block. Why is that important? Well, because every electron configuration short of 3D is going to be completely filled. So all I need to do, I don't need to count each one. I just need to know how many electrons go into it. And then I can just assume that maximum value until I get to the configuration that I'm interested in. And then I can count the number of boxes till I get to that element. So I start at the top, 1s2, 2s2, 2p6. Now again, where am I getting those numbers? Well, I'm getting them from the number of elements in each of those blocks. 1s2, because there's 2 in that block. 2s2, because there's 2 in that block. 2p6, because there are 6 in that block. And if your mind's kind of swirling around this right now, it's a pattern. Eventually, it becomes kind of second nature. S is 2, P is 6, D is 10, F is 14, unless I'm in that particular zone and I have to count. But otherwise, it becomes kind of automated. You just get used to it. So I'm going here to zinc. 1s2, 2s2, 2p6, 3s2 covers me to there. 3p6 gets me through argon. 4s2 gets me through calcium. And now I get to zinc. We're in the 3D block. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Zinc is the 10th in that group. So its configuration ends with 3d10. All right, the next one, complete configuration for argon. So for argon, again, we start at the top. So 1s2, then 2s2, then 2p6, then 3s2. Now argon is in the 3p. So we've got to count it out. 1, 2, 3, 4, 5, 6. Its last configuration is 3p6. The last of this group is scandium. We'll do this one in pink. Scandium is element number 21. It is a 3D, just like zinc is, but it ends obviously in a different spot. So again, we can kind of just go through the whole thing. Starting at the top, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and now we're at 3d, and scandium is the first element in that group, so it's 3d1. So when we're doing complete configurations, that's really all that we're doing. We start at the top, 1s2, and we just keep going down the periodic table until we get to the element that we're interested in. And then when we get to that block, we count the number of elements till we get to the element that we're interested in. And that becomes the last part of our configuration. Now, one thing you might be saying to yourself is, well, okay, I get this a little bit, but boy, doesn't this seem like a lot of writing. And we haven't even gotten to something like radon, which has 86 electrons in it. Isn't there a way to kind of shorten this up? And the answer to that question is yes. We can shorten this up using what's called a noble gas configuration. And in a noble gas configuration, what we do is we take that element that we're interested in. So let's look at scandium again. Now, scandium's configuration, we just had 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. We worked this backwards until we get to a noble gas. That noble gas in this case is argon. Now, we already did the noble gas, or we already did the configuration of argon. Configuration of argon was this piece here, leading up to the 3p6. In a noble gas configuration, we take this configuration that is the same as argon's, and we put that in brackets. So this part here is argon's configuration. Everything else is specific to scandium, 4s2, 3d1. And so with noble gas configurations, we can shorten any electron configuration by relating it to the nearest noble gas and then talking about how it is different from that noble gas. And that's really all that we have to do. So in your homework, you're going to see a little bit of this stuff. You're going to see mostly complete electron configurations, however. So what I want you to do, you're not going to be able to complete all of this without looking ahead, because some of those exceptions that I talked about are featured in the homework. If you want to go for it and try it, go ahead, read ahead. Look ahead at the next group of slides and try to make some sense of it from there. Otherwise, do what you can tonight and pick up the rest on Friday. And on Friday, we will finish up talking about electron configurations. And if there's time, we'll talk a little bit about trends. Otherwise, that'll be the subject of the supplemental video. On your way out, don't forget about the stoplight question so that you can get that participation point as well. Have a great day.